And this is Professor Shi. And Professor Lin Junliang. Professor Peng Dongkai. Professor Chen Hongyi. And okay, so before we let the four teams introduce themselves, let me briefly explain the rules. So the stage regulations includes the opponents first challenge the reporter for a problem and in 1 minute. And the reporter would decide to accept or reject the challenge in 1 minute. And once the reporter accepts the challenge, then the reporter has 5 minutes to prepare his presentation, and which would last for 12 minutes. And after that, the opponent has 2 minutes to question the reporter, and the reporter can answer some brief, and give some brief explanation to the opponent. And then the opponent has 3 minutes to prepare his questions. And after that, the opponent takes the floor. First, the opponent has 4 minutes maximum to discuss with the reporter. And the entire discussion will last for 14 minutes. And after discussion, the opponent has 1 minute to summarize the discussion. And the question, and then the reviewer would have a chance to question both the reporter and the opponent for 3 minutes. And after that, the reviewer has 2 minutes to prepare and 4 minutes to make his comment. And after that, after reviewer, then the reporter have 2 minutes to conclude, and then the 5 jurors have 5 minutes to question. Okay. So this will be the flow of the session, and then so before we start the fight, that's the captain of each team, please introduce yourself. So let's start with the reporter.
Here is the team activity, and as for the captain, I'm Lin Yongzhang. And as for my members, here is Guo Dazhao, Zheng Diyang, Wang Ruixi, and Chen Guoyu.
Captain of team itself here. My name is Chen Xuan. He is Liu Kaizhe. He is Chen Taihong. He is Chen Jian, and she is Wu Fangxie. Thank you.
From TYPT team, and I'm Huang Yujie. He's Li Pingyi, Cai Yilei, Ji Yaxing, and Wang Yanqi. Thank you.
I'm a test member of Team TYPT, and my name is Chen Shuya. This is Wu Yan, this is Du Rui, and this is Xu Han. This is Xu Hong.
So welcome to Capital University for this debate. And then let's start. So the opponent, you have 1 minute to challenge the reporter for the problem.
And I'm going to challenge the question, shooting rubber band.
The reporter accepts the challenge for the problem for shooting rubber band, and so each team will send someone to write down the name of your representative.
是不是没有教？
relativity, and today I'm going to report problem number 4, shooting rubber bands. As for the problem statement says that a rubber band may fire a longer distance if it is non-uniformly stretched when shot, giving it a spin. And we have to optimize the distance that a rubber band could spin and reach. So you can see from the observation here, if a rubber band is not evenly stretched, the distance of a rubber band will be longer. So my main focus of the problem will be the distance that a rubber band can reach with rotation and the different energy conversion efficiency of a rubber band in different conditions. So for how we shoot the rubber band, we shoot a rubber band in the x-axis, which is horizontal to the ground, and the rubber band here will be parallel to the table. So how does a rubber band spin? Because in our experiment, we fix the top of a rubber band in the center here. So because the rubber band was non-uniformly stretched, so the force of two sides will be different in the back of a rubber band. So after we shot it, it will have a spin of the back of the rubber band. So it can be shown by my experiment video. So for my modeling, I just simply compare the rubber band and the spring because the action of these two is very similar. So I want to check out if Hooke's law can be used in a rubber band. So in my experiment 1, I want to find out the relation between the outer force and the elongation of a rubber band. So I use the force sensor and the rubber band and use Excel and my computer to analyze the data. So this is my experiment data. So you can see that if the elongation is smaller than 6 centimeters here, the function of the outer force and the elongation wouldn't be linear. So the rubber band didn't match Hooke's law in this way, but if the elongation is equal to 6 to 12 centimeters, the rubber band here will be matched to Hooke's law. The outer force and the elongation will be linear. And K, which is the elastic constant, will be the slope of the function. It will equal to 0.17. So in order to let K be the constant in our experiment, all the experiment of my experiment will be done that the elongation will be in the 6 to 12 centimeters here. So for my experiment setup, first I just simply shoot the rubber band with my hand, but it's not easy to quantitate the elongation of the rubber band. So I make a launcher by using a vehicle, but you can see that the vehicle failure is high because the rubber band will jump into the top of the rubber band here. So I change the launcher by using a chopstick to fix the rubber band. So therefore, the rubber band will not jump into the top of the Lego, so it will be more stable. And because the launcher will move, so I use the stickers to stick it on the chair, and the initial length of my rubber band will equal to 6.45 centimeters. So after the rubber band was shoot from an initial height, it will down the horizontal projectile motion, which is the velocity of the rubber band can be described by the phenomenon here, and the R here is the distance of the rubber band, and H here is the initial height of the rubber band. So if the rubber band doesn't have a rotation, we can write down an energy transform formula into like this way. So the left side of the equation is the potential elastic energy of the two sides of the rubber band, and it will be transformed into the kinetic energy plus the internal vibration energy, which can be shown by the graph under here, and the energy loss. But just the kinetic energy will be given into the distance of the rubber band. So I let alpha equals to the kinetic energy divided the potential elastic energy, where is the energy conversion efficiency. So the physics meaning of alpha is how much energy transformed from the potential elastic energy to the kinetic energy. So in my experiment 2, I want to find out the relation between different alpha and the different elongation. So I use the high-speed camera and tracker to know the velocity of the rubber band. I use the electronic balance to know that the mass of the rubber band is equal to 0.32 grams. I use Excel to analyze the data. So this is the different alpha and different elongation and the graph in the experiment video. So this is my data, and you can see that when the elongation is equal to 6 centimeters here, the alpha will be small. This is because the rubber band here will be unstable. And when the elongation is equal to 8 to 9 centimeters, the alpha will be small too. So after my observation here, the sum of the energy will transform into the internal vibration energy. You can see from my experiment video. And when the elongation gets bigger, the alpha will get bigger. So after my observation, the energy transformed into the vibration energy will be smaller. So you can see from my experiment video. So after we measure the alpha, we want to measure the distance of the rubber band that is flat without the rotation. So the distance of the rubber band can be described by the formula here, and the mg and k here is all the constant. So I want to find a relation between the elongation, which is the L minus L0 here, and the distance of the rubber band. So this is my experiment data, and because alpha here isn't a constant, it's the function of the elongation. But I want to let everyone know the trend of the theory line, so I let alpha be the average in the theory line here. So you can see from my experiment data and the trend of the theory. So next, we want to discuss about the rubber band with rotation. So I let 80 equals x, we can represent the spin of a rubber band. And this is how I done my experiment. So you can see that if 80 x here is equal to L0, there will be no spin of a rubber band. And if the n is smaller, the initial spin of the rubber band will be bigger. So for the elastic constant, the k here will be proportional to what A divided L, which A is the cross area of the spring and L is the length of the spring. So in the experiment, the change of the area will be approximately the same, so k will be proportional to 1 divided L. And I want to do the experiment to prove that. So I cut my rubber band and mark every centimeters of the rubber band. And I put the same way under the rubber band and by the different length of the rubber band and backward the elongation of the different length of the rubber band. So this is my experiment data. So I feed the data with the k will be proportional to 1 divided L. And you can see the R squared here is equal to 0.97. So I think the formula here can be used in our experiment explanation. So next is the elastic constant. Due to the experiment 4, K will be proportional to 1 divided L. Therefore, KL, which is the elastic constant of the last spring, will equal to L0 K divided X. KR, which is the elastic constant of the right spring here, will equal to L0 K divided 2L0 minus X. So we can write the energy transform into another type. So the initial elastic potential energy of the left spring and the right spring will be transformed into a kinetic energy and a rotation energy and an internal vibration energy and an energy loss here. And because K will be proportional to 1 divided L, So we can write the KL and KR into the form under here. But as the same, just the kinetic energy will be transformed into the distance. So I let beta into the kinetic energy divide the potential elastic energy. So it's the energy conversion efficiency when the rubber band has a rotation. So in my experiment 2-beta, I want to analyze the difference between the x and the beta here. So this is my experiment data, and you can see that when the x equals to 4 to 5 centimeters, the beta here will have the maximum, which means that there will be more energy transformed into a kinetic energy. But when the x gets smaller here, which means that the speed of a rubber band gets bigger, the beta will be smaller. It's because some of the initial energy will transform into rotation energy, so that the energy transformed into a kinetic energy will be smaller here. So after we know the beta here, we want to find the relation between the x and the distance. So this is how I done my experiment. I use the marker here to mark the rubber band, so I can know the x, I can measure the x here. So this is my experiment data, and the constant here is at the top here. So because as same as the alpha, the beta here isn't a constant. So I let the beta be the average in my theory line. So this is the difference between my theory line and the experiment data. So the problem statement says that a rubber band may fly a longer distance if it is non-uniformly strapped with shot, giving it a spin. And we have to optimize the distance that a rubber band with spin can reach. So why will the rubber band fly longer? Because if the rubber band has a spin, some potential elastic energy will be transformed into a rotation energy, which makes the rubber band fly shorter, right? But this is wrong, because if the rubber band was strapped uniformly, the elastic constant of two sides of the rubber band will change because K will be proportional to 1 divided L, and we have done an experiment to prove that. So you can see that the initial elastic potential energy of the formula here will be different, and when the rubber band has the rotation, the initial elastic potential energy will be bigger. So the sum of the energy will be transformed into the rotation energy. The kinetic energy will still be bigger, which makes the distance of the rubber band will still be bigger. So for my conclusion part, there is a data of the distance that the rubber band fly with the rotation and without the rotation. And the x in the formula here symbolizes the rotation of the rubber band. And if the x is equal to L0, there will be no speed of the rubber band. And if the x is smaller, the speed of the rubber band will be bigger. And for the first experiment, I want to make sure both laws can be used. So if the elongation is equal to 6 to 12 centimeters, the function here will be linear. So the k, which is the elastic constant, will equal to the slope of the function, it will equal to 0.17. So in order to let k be in a constant, all of my experiment is done in the elongation being 6 to 12 centimeters. Next experiment, we measure the elastic constant change with the length. So I fix the k will be proportional to 1 divided L, and the R squared here is equal to 0.97. So I think that the formula can be used in our experiment explanation. And next, we define alpha beta to explain the energy transfer. And the alpha here is the energy conversion when the rubber band has the speed, without the speed. And the beta is the energy conversion when the rubber band has a speed. And this is the data of different alpha and beta. So this is the final conclusion of my rubber band of the theory line, because the alpha and beta here isn't a constant. It's a function of the elongation and x. So I just have the alpha being the average of all of the beta, so you can see the trend of the series. So the problem statement says that you have to optimize the distance that the rubber band with speed can reach. So you can see from my experiment data and the theory, when the x equals to L0, which means that the rubber band doesn't have any rotation, the rubber band will fly the shortest, and if the x gets smaller, which means that the speed of the rubber band gets bigger, the rubber band will fly longer. So this is all my presentation. Thanks for your attention.
So the opponent has 2 minutes to question.
Okay, so on your presentation on page 32, I need to page 13. 30.
Sorry, is page 30 or page 13?
30.
30. Okay. Okay.
So on the picture on the right, you have the R squared, which equals to 0.978. But do you think that your R squared value is enough to show that your to show that the equation is considerable or not?
Yes, because you can see from my experiment data and the theory, right? So the k will be proportional to 1 divided by L, and the R squared is 0.97 and it's very big, and there is some difference with my experiment. So I think the formula can be used in our theory.
Okay. Another question is that the rubber band may not slide straight. It may go into another direction. And when you measure how far it gets, do you measure the straight or how much did they went?
So I just measure the distance of the rubber band. So if it is stretched, and I just measure it, and if it is like go into another direction, and I will measure the distance of the rubber band.
Okay, time's up. The opponent has 3 minutes to prepare. Okay, the discussion section.
So I'm the opponent from TYPT. Okay, so this is a problem statement. place a spring, which the rubber band, whether the rubber band could match Hooke's law or not. Okay, so he has Hooke's law for the theory. And then for data analysis, he had whether he had the elastic constant change with the length. And the conclusion, he get that when x equals to L0, the rubber band will fly the shortest. Okay, so pros and cons of the theory. So first, the pros, I think he has a nice structure and good observation theory, and he did a well data analysis. However, about the cons, I think we could explain the equations more clearly. And also, some words in the PPT are too small. Okay, so for the first discussion, I want to ask that from my experience, after the rubber band length, sometimes the rubber band goes for more distances. So I want to ask, how would you consider it into your data? Also, the second discussion will be about if you shoot from different heights, actually the distance from the two are not because the distance you measure is from here to here. Actually, it's lower. So you give it some force to make it go down. Sometimes the rubber band may roll after it lands on the ground. So how did you consider it into your data?
So I placed a slow motion camera beside the rubber band, beside the place when we do the experiment, and the slow motion camera can watch the rubber band. So when the rubber band hits on the ground, we can know the distance from the slow motion camera.
So in your data, the distance is the distance is from where he landed, not more.
Yes.
Road.
So we know that distance that where he landed is the final distance. So if it's roll to the another position, it will not be the final distance.
Okay. Okay, so this is the second question. Like I just said, did you measure the length from two different places? Did you measure the length on the equal height, or did you measure the length from here to here?
Sorry, do you mention that it's the initial height of the rubber band?
Oh, I mean, how did you measure the distance between you have a height and the ground, right?
Yes.
How did you measure the distance between the table and this place? Did you measure this distance or the flat distance?
Oh, so in my experiment, I measured the flat distance because yes. So I used the ruler to measure the distance of the flat distance on the ruler.
Okay. Also, I want to know more about the camera, like the parameters of the camera.
So you mean the camera here?
Yeah.
The happy camera? Yes. So because there is the B here, so you can see from my equation here. So I want to know the B here, so I can measure the alpha, which is the image expression. So we use the high-speed camera to have the video of the object when it was shoot from the launcher. So after using the tracker here, we can know the velocity of the roller. So we can let it go velocity here and know the alpha, so know the different alpha.
Also, I want to know that in my experience, I searched one side of the rubber band, a very large much, but in your experience, you said that if I stretch the rubber band more, it could fly often, it could fly further. But actually, when I did the experiment, I found out that if I stretch the rubber band one side for too much, it actually couldn't fly. It actually couldn't fly as far.
So in my experiment, I strap the rubber band with one side, and the distance of the rubber band will just be longer. If I strap it so I just use the X here to symbolize the speed, right? So the X here is the length of the rubber band, also how to strap it. So in my experiment data, the X is smaller, the distance of the rubber band will fly longer. So this is my experiment data.
Would you think that the rubber band will fly shorter if I stretch one side of the rubber band too much?
Yes, because if it is into a limit condition, like if you just strap the rubber band is very tiny, so the rubber band may break. But in my experiment, I didn't let the situation happen. So when I strap it, the distance of the rubber band will fly longer.
No, I didn't mean that I let the rubber band break. The rubber band. My question is, the rubber bands may have, there may be some effects on our rubber band experiment. And how would you check your rubber bands?
So sorry, can you say that again?
There might be an effect on our rubber band in our experiments. And how would you check your rubber band?
So you mean that if the rubber band is different, the experiment data will be different, or?
Yeah.
Oh, so it will be different because the mass of the rubber band and the elastic constant of the rubber band will be different. So I can't use the theory line will be definitely the different one. So in my experiment, I all use the rubber band in the same rubber band. So the constant of the end, so the mass of the rubber band and the elastic constant will all be the same. So we can know that it will be a constant.
So like they are all new rubber bands.
Yes. So the rubber band in my experiment is all the same.
So about the rubber band spinning, why would the rubber band spinning make the resistance of the air decrease?
So you mean that because the rubber band has a spin, so it will be more stable. So the air resistance of the rubber band will be smaller.
Why?
So because in my explanation, the air resistance will be proportional to the cross area of the rubber band. Yes. So if a rubber band has the initial spin, it will be more stable because but the cross area of the rubber band is very small. So if it is more stable, if it is stable and non-stable, the change of the air resistance will not be very big because the cross area is very small.
So, if you consider the friction in your experiment, would you say it will be better? If you consider friction in your experiment.
So you mean that consider the air resistance or consider friction between the rubber band and the thing used to shoot your rubber band. Did you consider the friction between them? I didn't consider it, but because the air resistance wouldn't affect the environment very well. So it will affect the environment, but it can be ignored because it will be very small.
I mean the friction between the rubber band and the thing. And the thing used to shoot. You say you have the rubber band on the thing and you used to shoot the rubber band. And did you consider friction in the experiment?
Oh, wait a minute. So for my experiment, I do a launcher to shoot the ball right?
Yeah.
So I can know the experiment data. So I do a launcher, and the elongation can be fixed in our experiment.
I mean, did you consider the friction between the rubber band and the launcher? Would the friction influence the distance the rubber band can get
So you mean that the friction?
between rubber band and the launcher? Did you consider it? And would it affect your experiment results?
So can you tell me more about the friction? So what do you mean the friction here?
Friction. The rubber band and the launcher, and they have a force. So would you think did you consider it?
Oh, so in my experiment, so this is my launcher here, right? So this is my launcher here, right? And I use the chopstick to fix the launcher by using the chopstick. So the friction of the chopstick isn't very big. So but because the rubber has a spin, right?
Yeah.
If it is non-uniformly stretched. So the friction of the top of the launcher here will be big enough to have the friction that the rubber won't go to the not stretch, not uniformly stretched. Yes, what I see.
Also, back to the question, that is, you have the rubber band flying down from some height. Then, did you consider the angle between this and this? There is an angle between these two heights, right? If you connect these two and make a line, there's an angle between the line and the ground. Did you consider the angle?
So in my experiment, I didn't consider the angle here because the angle here wouldn't like it is not a variable that you have to consider in my theory. So I didn't measure the different angle.
Also, you have about your launcher. Would it be higher? You say you have you connect the rubber band with one side of the launcher. Is the side of the launcher and where it flew out, is it the same at the same height? Would it be higher? Like if the launcher is like this, but you connect the rubber band, maybe you have some, maybe it's higher. Would it be higher?
No. So we place the launcher on a horizontal table. So when the ball was fly up, it will be horizontal to the ground.
Okay. The only have 1 minute to summarize the discussion.
So after discussing about this question, we have some results. Okay, so first we have that if the more we uniformly stretch the rubber band, it can flow further. And also the rubber band may flow higher if we jump it from a higher height, like from a table, we can get a further distance. And
Okay. And the reviewer talks, you need to question both the reviewer and the reporter.
Okay, question for the both of you. Why the shape of a rubber band is more stable during a flight if the rubber band is not uniformly stretched?
So because the rubber band has a spin, right? So it will have so it will be more stable because if it is not stable, the air resistance lack influences, so it will be not stable. But if it doesn't have a spin, it will have an angular momentum, so it will be more stable.
So,
I think if it's uniformly stretched, the rubber band will spin. So the spinning will make the air around him go through around him more equally. So the rubber band can flow more fluently further.
okay, thank you. So, next question, question for both of you. Will the rotational velocity of the rubber band change during the flight, and why?
So you mean an angular velocity?
Yeah, angular velocity.
So it will change a little because of the air resistance, but the change of the omega will be very small, so we didn't have to consider.
Thank you. So,
I think it will change because during the flight, I think that the energy will decrease. So I think it will change.
okay, thank you. And question for the opponent. What happens if you shoot rubber band vertically?
If I shoot it vertically,
Okay, thank you. So, question for the reporter.
So you mean shoot it in a vertical axis?
Yes.
So when you shoot it in a vertical axis, you will have a magnetic force to attach to the rubber band. So it will fly out. If you shoot it in a sideways like a cycle, so you will suffer a magnetic impact.
Okay, thank you. Question for both of you. Which has a greater impact on the distance? Is it elongation or the rotation? Opponent first.
I think that rotation has a greater effect on the distance we can get. I think that the rotation can greatly decrease the air resistance on the rubber band. So I think it can get further.
Okay, thank you.
So if the elongation is bigger, the rubber band will fly bigger, will fly longer. So if the rotation will impact is that if the elongation is fixed, the more of the rotation will make the rubber band fly longer. So it's the situation.
Okay, question for both of you. How do you think
Okay,
the size of
the time is up and the viewing 2 minutes to prepare. Okay, you can start.
Honorable jurors and fellow competitors, I'm the reviewer from Team Excelsior. Today I'm going to review problem 4 on shooting rubber band. And this is a problem statement. Main focus is investigating how spinning affects the distance that rubber band can reach and how the different parameters affect the range of the rubber band. first a review for the reporter. First, the phenomenon part, he shows the spinning rubber band will fly more stably during a flight and reach a longer distance. And in the theory part, he explained the Cook's law and energy conservation and the rotation theory. And the experiment part, he explained the he investigated the relation between elongation and distance. Experiments from normally stretched, unevenly stretched, and elongation and degree of uneven stretching. And the strong and weak point. The reporter demonstrated the phenomenon well and have a detailed theoretical model and explain the boundary limits, and he have a clear explanation on graph, and he have a clear theory line. However, he had not much explanation on his deviation in the experiment, and his observation video is too small, and it's so I think it's unclear. Also, he had an unclear chart about the experimental data. And the review of opponent. First, they notice the lack of illustration of structure, and he had detailed discussion on the track of a rubber band. And he noticed the flying distance won't be straight during the experiment. However, he didn't discuss the sliding situation and not mentioning clear quantitative explanation depends on the parameters from the reporter. The most important thing is he has a wrong process and didn't get discussed on the theory well, and he has poor time control. Key discussion. The opponent asked, would you think if a rubber band is out of its elastic limit, will it affect the distance? The reporter said yes. And the reviewer agreed with the reporter because the reviewer believed that if a rubber band is out of its elastic limit, its distance will be decreased. And the point is, our question, which has a greater impact on the distance, elongation or rotation? The reporter said the elongation bigger, and the opponent said rotation can change and optimize the distance. The reporter agreed with the reporter. And the point is, in the theory part, they didn't discuss about uneven stretches, normal stretches, and the potential energy in the rubber band and the air resistance didn't take into consideration. And in the experiment, they didn't discussion about elastic boundaries and the measurement of friction
Okay, the time is up.
air resistance. Thank you.
And the reporter, you have 2 minutes to
Here is the
conclude.
concluding remark. So there is a public statement in my report. I model the spring and model the rubber as a spring and use Cook's law, energy spectrum, and horizontal projectile motion to describe the phenomenon. And for my experiment setup, there is a launcher, so I can make sure that the elongation is fixed in my experiment. And so the discussion with the opponent is that the opponent asked me if the R value is enough to show the equation. And my explanation is that it's very close to 1, so it's very reasonable. That is 100 for the rubber band flow. So I use the slow motion camera to know the distance. And the R here I measure is the first hit on the ground. And the third is that you measure the distance, so I may measure the flat distance on the ground, so it's an R here. So next is what is the parameter of the camera. So I use the camera and the tracker to measure the velocity and to know the alpha, which is the energy conversion in my experiment. So how to check the rubber band elastic is constant. So we use the same rubber band and can prevent that the elastic constant will change in our experiment. And next is that the reviewer asked me if every system will affect So in my opinion, the air resistance will affect little to none because it can be ignored. So the consider of the angle of the drum and the launcher is not proper, it's not a parameter that will affect. And will the angle velocity change? It will basic change because of the air resistance, but it will not change a lot. So what happens when shot in the vertical? It will suffer some magnetic effects, so the rubber band will fly longer. So this is my presentation. Thank you.
Okay.
We have 5 minutes for juries to ask questions.
Question for all 15. The same thing is, what's the most important factor for the rubber band to shoot longer? Is it elongation? What is elongation? So starting with
So I think that the more important parameters in our program is the rotation. So I use the X here to represent the rotation. So when I shoot the rubber band in the horizontal way, so I just drag the rubber band into like this. So
okay, so you said rotation is the important thing for them to fly longer.
Yes.
So how about the opponent?
I think the spinning of the rubber band is the most important efficiency. I think the spinning of the rubber band can decrease the air resistance from stopping it from flying further.
So swing can reduce the air resistance. So air resistance is the most important thing. So how about the
The reviewer believes is elongation to affect the distance of the rubber band can reach, because if a elongation is too small, even if it is spinning very fast, the distance won't be very far. The elongation is, so I think the elongation is the most important parameter.
Okay. Yeah, I have a question for you and that you are talking about the height, right? So if we do the experiment on the floor or on the 3 meter high, will that affect the result and stuff?
I think if we shot the rubber band from a height, I think it can fly. I think the track of the flying may be influenced more. I think the rubber band may come, and the result of the rubber band may come in more ways.
So in my experiment, the initial height of the rubber band is equal to 0.5 centimeters. But I think that if the initial height is bigger, so the time that the rubber band will fly is will be longer. So the air resistance that's given to the rubber band will increase. So it will affect. But I didn't train the initial height, so I didn't measure the parameters here.
So in final question for you're talking about the shooting vertical. Do you think that would be the better way to start this program?
I think if a rubber band spin vertically, I think it will, because of magnet effect, the rubber band may fly up and fly straight up and fly a longer distance. So I think shooting vertically may be a good way to optimize the distance that rubber band can reach.
Is there any other question? Okay, now that's prepare the score. Huh? You want another question? Oh, okay. Professor.
That's a short question. You consider the spin constant of rubber band as constant. Would the temperature be a factor?
So the temperature will affect the elastic constant of the rubber band. But in our experiment, the change of the temperature isn't very big. So I just simply that's the elastic constant being the constant in my experiment explanation.
Did you reuse the rubber band?
Yes. So all of the experiment data is all used in one single rubber band.
So they will heat up the rubber band.
So yes, so it will heat up. So the data every data, the time of by doing the experiment will take like the 3 to 5 minutes. When I do the experiment, so I just let the rubber band cool down.
So what about component? Do you think temperature is important?
Yes, I think it affects very small. Yes, it's very.
I think temperature is an important part to consider in the deviation because the rubber band
Okay,
may.
your time is up. Let's prepare the stove. Let's show the score for the reporter. 6. 6, 6, 8, 8, 8. And then the score for the opponent. 6, 5, 4, 6, 6. And finally, the score for the reviewer. 7, 7, 6, 7, 6. Okay, so because we have 4 teams, so let's just make the break for 10 minutes, okay? So in the meantime, during the break, please exchange your contributions.